Quick test of your thinking. You meet a man named Charles. Charles is quiet, introverted, and enjoys reading. Based on this description, would you guess Charles is more likely to be a librarian or a salesperson? Many of us would immediately think librarian, given the stereotypical traits associated with that job. But we'd be wrong. Charles is most likely a salesperson, and we've just fallen into a common cognitive trap, the base rate fallacy. The base rate fallacy occurs when we ignore general statistical information in favor of specific or prominent details. In this case, we may have overlooked the fact that there are far more salespeople than there are librarians. Even though Charles's personality seems more suited to a librarian, the fact that salespeople vastly outnumber librarians suggests that he is more likely to be a salesperson. This fallacy stems from our tendency to favor specific information rather than statistical data. Let's break this down further. Base rates refer to how frequently something occurs in the broader population. Base rates represent general probabilities that should form the foundations of our decisions. However, when we are given additional details, especially those that seem important, we often focus on these specifics and forget the broader statistics. This is why we focus on the description of Charles rather than the number of salespeople compared to librarians. Let's explore another example. Imagine you're a doctor evaluating a patient for a rare disease that affects 1 in every 1,000 people. There is a test available that correctly identifies the disease 99% of the time, but with a 1% chance of returning a false positive. You run this test on your patient, and the result comes back positive. Should you be 99% sure that your patient has the disease? Well, no, and here's why. Even though the test is highly accurate, the base rate of the disease, how rare it is, plays a significant role in interpreting the result. Because the disease is so rare, there's a good chance that a positive result is actually a false positive. For every 1,000 people tested, only one person is likely to have the disease. But with a 1% false positive rate, around 10 people will incorrectly test positive. This means that the likelihood of your positive test patient actually having the disease is much lower than 99%. It's closer to 9%. When we focus solely on the test's accuracy without considering the base rate, we make a logical mistake. Let's clarify this further with a different example. Imagine a city of 1 million people. Authorities install a facial recognition surveillance system, attempting to identify known terrorists. In this city, only 100 of the inhabitants are terrorists. All other people are regular citizens. If the facial recognition system scans a terrorist, the alarm will sound 99% of the time. If it scans a regular citizen, the system will incorrectly sound the alarm just 1% of the time. At first glance, this system sounds impressive, but there's a problem here. Now, let's assume the system is triggered, signaling that a terrorist has been detected. We might immediately conclude that the probability of this person actually being a terrorist is 99%, based on the system's accuracy rate. However, this reasoning ignores the crucial factor, the base rate. We need to consider the actual proportion of terrorists in the population. Since only 100 out of 1 million people are terrorists, the base rate of encountering a terrorist is extremely low. Imagine if the entire population walked past the surveillance cameras. With the system's 1% false positive rate, that would mean 9,999 non-terrorists falsely trigger the alarm, compared to only 99 actual terrorists. So, Despite the high accuracy of the system, the chance that someone who triggers the alarm is actually a terrorist is less than 1%. This is a classic example of how the base rate fallacy leads us to overestimate the probability of an event. By focusing on the accuracy of the system, without considering the proportion of terrorists in the population, we fall into the trap of the base rate fallacy. Let's look at one more example to solidify our understanding. Imagine a hospital in a small town. During the height of the COVID-19 outbreak, the hospital admits 5 unvaccinated people and 10 vaccinated people. From this, would you conclude that the vaccine is ineffective or even dangerous? Let's zoom out and look at the base rates. In this town, there are 5 other unvaccinated people who didn't get admitted to hospital, but there are also 90 vaccinated people who also weren't admitted to the hospital. When we look at the base rates, we can conclude that the vaccine is actually quite effective. As these examples demonstrate, when we fail to consider the broader statistics and instead focus on the details, we are easily misled by the base rate fallacy. So how can we avoid this cognitive trap? The key is to stay grounded in the data. When making decisions, it's important to factor in the base rates first and then weigh any additional information. We need to consider the broader statistics before we get caught up in any specifics. Another helpful approach is to quantify uncertainty. If you're making a prediction, try to express it in numerical terms. Ask yourself, how likely is this outcome mathematically? This forces you to confront the base rates and can prevent you from overemphasizing subjective details. In conclusion, while personal details and vivid stories often grab our attention, we should remember to consider the bigger picture. The base rate fallacy highlights how easily we can be misled by specifics, while ignoring the broader context. By keeping base rates in mind and grounding our decisions in data, we can make more accurate judgments and avoid the pitfalls of focusing too much on the details.